ja vás vítam, aj keď v nejakom malom komornom počte, ale myslím, že to je dobré. Chcel by som urobiť najprv nejaký taký malý stručný úvod. Chcel som povedať, že my, ale v princípe ja a ešte nejakí moji kolegovia po svete sme sa rozhodli, že spravíme jednu platformu, ktorá sa volá iPub. Web stránka ešte nie je, ale pevne verím, že cez sviatky ju nejak dáme dohromady. A mala by byť venovaná diskuzii a stimulácii diskuzii o umelej inteligencii. Takže ja teraz prejdem do angličtiny, aby ostatní tiež rozumeli. So I would like to welcome you here, and we decided with my colleagues from China and United States to set up a platform called iPub, which would be something like a platform for discussion about AI. There are several other discussions around the globe, but I would like to promote with this two organizations. One of them is IEEE. So if you students are not members of IEEE, I would really recommend you to be a member. The membership fee is about $27 for student. So if you want in the future to be in the domain of development, research, or something like that, then I would really recommend you to be a member. Once again, $27 is lots of money. That's not lots of money per year. So try to think about this. IEEE is a world organization, about 600,000 engineers worldwide. This is one. And second is CIC. CIC is special subgroup of IEEE devoted to computational intelligence. So this is a worldwide. They have a headquarters in USA, and trying to put together engineers and experts in the domain. And recently, there was established an International Association for Computational Intelligence with headquarters in Hong Kong. So I think you all feel that also China is coming into the play, and China is in fact leading this organization. But it's a global organization, and if you want to be a member of this organization, it's free. Later on, if you are interested, I can give you some information how to become a member. Once again, the second organization is free. These two organizations are going to be in connection and in collaboration. They should support each other. So I hope that it will be for benefit of all the AI community. So today's seminar is about work of two our students. One of them is master student. That's Mr. Ruzmetov, and he will be talking about diffusion model, and maybe I'm sure that you know that diffusion models are very important in generative AI. And second one is Mr. Uhrynchuk. Viktor is working as a bachelor student in the domain of multimodal neural networks. And multimodal neural networks is a domain where we probably, for 99%, we will have some small project starting next year for 4 years. So that's why I would like to push this multimodal neural networks, which are very interesting, and they can be very influential in neural network domain. Okay, so I would like to start, and I will ask Mykhailo come and say his first talk. It's scheduled about 30 minutes, so I hope it will not be boring, and you can generate questions as well.
So I can start. Okay, so my topic is about diffusion models. During this presentation, I will be mainly talking about the intuition behind diffusion models, not going deep into mathematics or complex subjects, so everybody understands what it is and gains like enough understanding to going deeper themselves into proofs and, as I mentioned, mathematics. So firstly, let me just give you a quick overview on what the diffusion models are. So the diffusion models consists of two processes or two stages. The first stage is the forward diffusion, which is gradually adding noise to some kind of data. It's usually images. And the reverse diffusion is the opposite. So when we have pure noise, let's say, it is the process of removing such noise from the data or from this image. So yeah, let's go to the next slide. Next, I just want to give you a quick comparison between already existing and established models for generating data. So first, I will start with the diffusion models because it's our main topic. The diffusion models have a high quality data, generate high quality data with a high diversity. If it has a lot of classes, it won't fail. Like it's gonna be still pretty good. It still show pretty good results. And the main disadvantage or the main downside of diffusion models is the time it takes to generate a single sample. And now comparing to GANs also have a high quality results, but unfortunately they struggle from a low diversity in classes. So when you train a GAN on many classes like 100 or 500, it's only gonna generate a few of them really good, but the remaining part will be quite bad, I think. But still, GANs have a pretty high sampling speed, which is a huge benefit for them. And the last one, variational autoencoders. They struggle from a quality from a low quality of generated samples. But on the other side, they have a high diversity, so they are really good for representing multiple different classes. And they have high sampling speed, which is also a huge benefit. And also, I think they have pretty much the highest speed among all these three models. So that's about the comparison. Okay, so firstly about the intuition behind the diffusion models. So diffusion models, they work with a data distribution, which of course we can simplify and visualize, which is a huge benefit for understanding and like explanation of how it works. Here you can see on this graph a two-dimensional space which contains these four blobs or clusters, which represent our valid data for different classes. So outside of these four clusters, the data is invalid, and it's basically a pure noise. But inside of these clusters, it is a valid, let's say, image or like any kind of data sample. So firstly, I would like to explain a sampling algorithm. So sampling, firstly, takes a pure Gaussian noise, samples a pure Gaussian noise, then it refines this noise, this Gaussian noise, for a certain amount of steps until it is a pure data sample. For example, on this image where we get a cat from a pure noise. And in context of our data distribution space, it will look like this. So it will start in this invalid data position, and will gradually move to the valid data data cluster. For example, you can imagine these are cats. So it's gradually moving to this validity, and the model, that is what is guiding this this sample to get to this valid state. Okay. So the next one is, we understand now how the data is being generated, or like on an intuition level, but how is it actually trained? So firstly, here is like an algorithm described in text, but then I will show you the visualizations for this. So firstly, we get a batch from a training data, let's say 16 samples of images. Then we assign a random time step for each image. And this time step will determine how much noise is going to be added to this image. So a bigger time step will mean more noise is going to be added. And yeah, the third step is adding the noise. So after that, we use our diffusion model to predict this noise by feeding noisy data to the network, and also the time steps. It can be a number, or it can be also a vector. Usually it is a vector. Okay, so for the next slides, I will be showing you a few examples of the application of diffusion models in different domains for different kinds of data. And then I will show you a quick example of my diploma thesis, which is about generating neural network weights using diffusion models. Okay, so firstly, I need to mention it. Diffusion model is a universal framework, so it's not only made for images or like static. It's not static. It can be adjusted for anything, basically. So it doesn't care about the type of data. It needs to know, firstly, how to add noise to a data. Then it needs to be capable of removing this noise from data. And the third thing, the data has to be learnable. It has to have a nice structure that can be learned by a model. So it can be chaotic or random. So it's gonna just mess up the model's results. Here are two examples of how a diffusion model is used across two domains. Firstly is biology and chemistry, which here, in this example, it generates different proteins. And as input it takes, I think it's taking some constraints, some chemical, biological constraints to generate the desired proteins. And on the right, you can see the 3D modeling example, which also uses a diffusion model to generate a mesh or a full 3D model with polygons that can be used in games or, I don't know, in modeling. And it takes a point cloud, which can be generated just from your camera. If you have iPhone, you can just scan some object and it will give you a point cloud, so you can generate a 3D model from this. Okay, so what is making this possible to adjust this diffusion models for different kinds of domains? Firstly is data representation. We really need to think about how a data is represented when we try to introduce our diffusion process to a new field. For example, in images, the images must be encoded firstly using some kind of network, or if it is text, the text must be embedded and like tokenized, and like there are a lot of things about the data which we need to think about. Second is the architecture adaptation. Usually, diffusion models use units and modified versions of units for different kinds of tasks. But if you have a super specific task that cannot work with a unit, you can come up with a completely new architecture. But of course, it's going to be super complicated if it's a new architecture. And third is the conditioning mechanism, because our data, our domain, it needs some kind of input on which it's gonna be basing its generating results. So, for example, for images, it can be prompts, it can be classes, but for, as I mentioned before, the proteins, it may accept the structure or the constraints of biological constraints to generate desired proteins. So that's also another thing to think about. So here is, so I will just give you a quick showcase of my diploma thesis for generating neural weights. Firstly, an overview, a model overview. The model itself called recurrent diffusion for parameter generation, which of course generates parameters for any given model, given a structure of this model. And in the paper, it scales up to 200 million parameters on a single GPU, which is not, of course, your regular GPU. It is A100, which is a specific kind of GPU for tensors and AI. But still, it's pretty impressive. And I also tried it on my, I tried it on A100 to generate, I think it was a visual transformer architecture, and it only took 3 or 5 minutes to generate, which is quite impressive. Third is, it was tested across multiple architectures. It was ResNet, I think 101, or yeah, I think 101, visual transformers, ConvNext, and of course LoRa, which is a fine-tuning technique for LLMs. It generated these intermediate layers for LoRa, so that's pretty impressive. So generative models, of course, they achieve a pretty good results for in terms of accuracy. They're pretty good, and they are not missing much accuracy from synthetic samples. And sometimes there are some cases when the accuracy actually grows in generated samples. And lastly, it can generalize to unseen tasks, which is also pretty impressive. It can basically generate tasks that it haven't been trained on, but that are still pretty close to the initial ones. Okay, here is the architecture. I will briefly explain what is happening. So the first part here is parameter processing, which we basically take all the parameters from our network and we tokenize them into fixed length tokens. So let's say each token it is 8,000 contains 8,000 weights. And we basically split this into this 8,000, each 8,000 weight is gonna be a single token. And if the token is shorter, when we take this token at the end, this weights at the end, the token is going to be shorter than 8,000 weights. So we are adding a padding, so we do not skip to the next layer and capture the next weights, because it's gonna just disrupt the generating process, and the model just won't understand why we actually skip to some kind of weird numbers there, which it doesn't understand. It's the next layer. So that's how it's done. And second thing we have here is are the position embeddings, which represent firstly a position inside each layer, each token. It represents a position of each weight inside each layer, and it also represents the position of the layer itself. So it has two values, and also it encodes these values using sinusoidal 2D positional embedding. And second, we have here an actual model. It uses two parts. The first part is a recurrent model, which can be actually an LSTM or even a transformer, which is not a recurrent model, but it still can generate sequences, so it can be used. But in the paper, they used a MAMB architecture, which is really efficient with long sequences of tokens in terms of time to process all of them. Okay, that's basically it. They also have this conditioning, which is a permutation state, which I won't go deeper into this. It's really specific part for this architecture, but yeah, they use it here. And also this 1 and 7, they are pretty much classes here, represent classes. Okay, here are some results from the paper. So for this experiment, they took a CIFAR-10 dataset and generated different combinations of classes to be classified by some kind of network. And for a training set, they took like 80% of these combinations, and for validation, they took like 20% of unseen combinations, which the network wasn't trained on at all. So it didn't see at all like all of these combinations. And in here, in the results, they basically fed to the network these unseen embeddings of the combinations of classes to be classified. And as you can see, the accuracy is really good. Like from 97 in the original weights, it just got lower by 3% in the synthetic weights, which it generated from this embedding only. So that's pretty nice, nice demonstration of the generalization capabilities of the model. Okay, so right now, quickly about my experiments, what I did on my own here. So my plan for the first experiment was to generate weights for various deep reinforcement learning agents. Each agent will be conditioned on a specific behavior. For example, you can tell an agent to go faster or to be more careful, or to, in the case of this landing guy, to use less fuel. That's one approach. And the second approach is to condition it on an environment specifics. So you can increase the gravitation, or you can decrease how do you call it? The friction of the surface here. So yeah, it will be more slippery, and like many other interesting approaches. And yeah, these problems are called. This one is bipedal walker, and the second one is lunar lander. So right now it's not super good. I don't have like great results from the synthetic weights, but still it generates weights that are capable of moving this agent forward, even though it is pretty slow, but it's capable of generating working weights already. And right now I'm mainly looking into like different small problems that may result in the poor quality of the generated weights. And in the future, I think I'm pretty close to solving it, and then I will switch to another problem in the reinforcement learning. So that's basically what it is right now. Okay, yeah, and thank you so much for your attention. And if you have any questions, I would be happy to answer.
Okay, so any question before you will thinking about a couple of those? Could you come to the second slide?
Second slide, yep, of course. Okay. Second, 765. Third, second.
Second, go ahead. One more.
Okay.
Okay, go back to this first one.
This one?
I mean, yes. I just want to, just a note.
Yeah.
Bidirectional and autoencoders. One of the first, when they were thinking to switch from real numbers to distribution, probability distribution. That's very important, that you have to realize that we are working with distributions because it's all about statistics. That's what.
Yes.
Okay.
Mm-hmm.
Yes. So here, dimension 1 and dimension 2. These are features.
Yes, those are features. If it was about images, for example, if we have 200 by 200 image, it's gonna be like 40,000 dimensions here. So, so that's how it is usually in diffusion models. But here, for example, I took just 2 dimensions.
It's some kind of a feature space, right?
Yes, it's a feature space.
And these are clusters in the feature space.
Yes, but it's in real life, of course, it's gonna be usually colliding together. It's gonna have different shapes. Yeah.
I mean, in fact, you have here 4 images.
Mm-hmm.
And the rest of these 4 clusters are some chaotic images, what we don't really understand. Right?
Yes, all of these that are not in the clusters are pure noise, basically. Pure noise, yeah.
So, in fact, what we are doing, we are noising it and then denoising it to the real image.
Yeah, so we are basically starting off this cluster. By noising it, we are just moving across this space to some random point, and our task is to predict a direction in which to go to reach this initial cluster.
Now, what you told is a training.
Yes, it is training.
It's trained, then you can start anywhere you want
Mm-hmm.
and try to find the real image.
Yes.
That's a secret behind the generation.
Yeah, exactly.
Because frankly speaking, I didn't understand how it can generate from the noise image. But before it was trained that from the real noise, the real image, it went out to the noise world, and then it was trained to come back to the image. Please confirm it if I.
Yes, you're completely 100% correct. Yeah, it is how it works.
Because nobody understands how it can generate image. But it's not about generating image. Before it was trained, go from the image to the noise, and then from the noise back to the image. And now when it's already trained, so you are coming back from the noise to some kind of image. Okay, go ahead. That's a nice example about the scat.
Oh, okay, let's go.
You have completely nothing, and you come back in that big feature space. You come back to the place where the image of cat was. So that's really nice. Okay, go ahead. One more.
Mm-hmm.
Yeah, this again. This is a training space.
Yeah.
I mean, the feature space. In the feature space, you find the clusters when the real images are.
Mm-hmm.
Okay, go ahead.
Go ahead.
One more.
Okay.
Okay, that's inspiration. Okay.
Yeah.
I just go ahead. One
more. Mm-hmm.
One more. Yes. Yes. This is very interesting that, in fact, this idea of generation can bring some new image. In fact, so like, I don't want to say new protein, but new image. So if you are in the noise and you are coming to the trained already image to okay, go back. I want to.
Yeah.
Wait. I try to explain it maybe here. So I was training to 4 images, and in fact I went out and I was going back, right?
Mm-hmm.
Now what else? What happened if I don't know that here will be something new, some other image? Okay, so if here will be some reasonable image, then I can generate it. So if I go back,
Oh, it's in painting mode, I think. Not sure. Yeah, the problem is we only control right now. I don't know. Oh, okay.
Now he tends to go somewhere here, but what if he comes here and here is something what we've never seen before? And that's what I'm saying, that
I think it's working right now.
okay. Go ahead. This protein I want to see.
Mm-hmm. This protein, yep. This one.
What happens if from the noise he generates something new, which makes sense? So you should realize, or we should realize, that it's not a miracle. It's just going to the escape of the noise and coming back to the real problem, but we never know when we can find something new. And that's why it's good that we have a HPC center, because it needs lots of power for computing. Okay. So and I don't know if you realize what is his goal. And please confirm it.
Mm-hmm.
He wants to generate weights for neural network. So in fact, you want to rebuild you want to come up with new paradigm of training?
It can be. I think it's more closer. It's closer to transfer learning. When you think about it, you take a lot of models to train this diffusion model, and then this diffusion model generates basically full working weights from a lot of trained neural networks.
As far as I understood, you have some topology.
Yeah.
And you are not training this topology by standard gradient descent.
Yeah.
You take this topology, put it into neural network, and this neural network will generate you 1 million weights.
Yes.
I mean, it's a huge shift in the paradigm, because if you can do it, I think it will be very interesting, because then maybe you can. I'm not sure if speed up. It can maybe bring. The interesting question will be that if you have generate 1 million weights, if you can learn from this generation of 1 million weights, then you will have to generate 2 million weights.
Okay, I'm not sure, to be honest. Like, if I generate million weights for what exactly?
For neural network.
Yeah.
And now you come a different task. You have to generate not 1 million, but 2 million. Then you learn from the previous 1 million training something for this 2 million training.
I think the same model probably cannot learn from its outputs. It should learn from from actual weights. But if we, for example, use this generated samples for for training another model or another architecture or something, it might work. It might work. But training the model with its own weights, it's like training a diffusion model on its own images to generate better images. It's probably not gonna be the best, but yeah, it's possible, I think, for in specific situations. Yeah.
You understand what he's talking.
21st. Okay, sure. The first. Yeah. Yeah. Back. Here. Mm-hmm. Yeah. Not really. I can explain on this architecture, this one. So firstly, our first stage is preparing the weights. So it's basically a dataset preparation. The tokenization is happening deterministically. It doesn't have any learnable things or whatever. It just splits the weights into fixed sized, batches or tiles or whatever. And then it also adds these positional embeddings, which also it's similar like in the textual processing tasks, like in transformers, we're just using sinusoidal embeddings for positions, but here we encode actually 2 positions. After we get our dataset tokenized, so it's all sequences of tokens and sequences of positions for each token, we send this we do not send the actual weights to the recurrent model. We only send the positions to the recurrent model. So it can generate, in this intermediate step, it will generate prototypes, which will represent abstract structures of the whole weights. So depending...
Like initialization, like starting?
Yeah, it's basically a starting for our diffusion process. So the diffusion will understand from these prototypes what kind of structure this network will have. So it's only like representing the structure of the network, of our future network. And after we generate the prototypes conditioned on the classes, for example. So if you want cats, it will generate a structure specific for cats. The diffusion process will take these prototypes as a condition. So it's going to be conditioned on these prototypes, a sequence of prototypes, and little by little it will generate or refine these prototypes into fully working weights for our application. So that's basically how it's going to work. And during training, we will take these predicted tokens and then just compute a loss between the predicted tokens and between the tokenized, our initial tokenized ground truth tokens. So it will just compute a mean square error. And when performing a backpropagation, it's gonna go from this loss, it's gonna go to the diffusion models, adjust the weights in the diffusion model, and then it's gonna also go backward to this recurrent model and will adjust the weights in the recurrent model. So it's a pretty smart way, because we basically train from our diffusion model also diffusion and a recurrent model. So it's training both models using only one loss. And that's the way how this model learns how to produce correct structures for our future weights. Hopefully it's understandable.
Okay, so in fact, it's not about avoiding standard gradient.
Yeah.
It's shifting standard gradient to the weight generation.
Yeah, we are using it for training the whole generative model instead of using it for training.
You are not avoiding standard gradient.
No.
You are just shifting standard gradient in different positions.
Yeah, it's just using basically, it just trains these 2 models to understand how the weight space is looking like pretty much.
Okay. Any questions? I think we are running out of time, but I think it's an interesting domain and topic. So maybe you can contact and be in touch. Maybe also for the audience. It's interesting to study these future models. Okay, thank you, Mykhailo.
Thank you.
So now Viktor will do the second one.
So, good day everyone. My name is Viktor Uhrynchuk, and today I would like to present to you basics of BLIP2 model and multimodal models overall. My main task was to explore multimodal models as a concept. What are they used for? What are their types? And in an example of Blip2, show to you how they work and how can we use them. This is a very rapidly growing part of AI technology because it can combine natural language and visual queries together in an effective way, which allows us to extract meaningful representations from the image and comprehend visual data and text data, bridging the gap between seeing and understanding. On this image, you can see a quick, simple example of usage of the multimodal vision language. We have the image as an input, question as an input, and the model gives us the answer to our question based on the image. So many researchers and enthusiasts for some time thought, how can we simplify the process and combine together vision and language in an effective way, so we wouldn't have to spend a lot of time, of money, and computing power to train visual encoders and large language models. So they decided to create a lightweight bridge between them, connecting both of them and freezing the large language models and visual encoders. And that's pretty much how Blip2 work. What is Blip2? It stands for Bootstrapping Language Image Pre-Training. It uses a big image encoder, for example, visual transformers L or G, and a large language model, OPT or FLAN. And using the strength of these two parts, it connects them with a bridge called query transformer or QFormer, so that from an image input, we can pass the image information to the large language model without having to train each of these parts, and in a way that large language model can understand images because it formats them in a specific way. I will cover it next. So this presentation will cover multimodal models, Blip2 architecture, how it works, how is it trained, its advantages, disadvantages, trade-offs, and performance improvements. So let's start with multimodal large language model explained. There is no single universal way to create a multimodal large language model, but we can put out 5 main key concepts. It's modality encoders, input projector, LLM backbone, output projector, and modality generator. These two, the last one, they are not used in every multimodal large language model. For example, in our Blip2, we use only 3 first ones. It's modality encoder. We use raw data. We can use images, 3D audios. In our example, we will use images. We pass them through to the input projector, which aligns encoded features and its queries to be compatible with the large language model and extract the main features from the input data. They're then passed to the large language model backbone that can work with the output of the input projector and generate captions, explainings, some creative text based on the starting input. After LLM backbone, we can pass it to the output projector, which will map the LLM outputs to the features which are suitable for modality-specific generators. And in the end, we can have a modality generator, which can produce outputs in non-textual modalities, like images and audios. but we'll cover the three main types of multimodal large language models. The first one, like the BLIP2, is vision language connector. It's a popular approach, the most efficient one, the most cheap one, the most fast one, but it has its disadvantages. The way it works is that we take the frozen image encoder, and large language model is also frozen, build a lightweight bridge between them with some trainable parameters, and this key component connects two of them, as I described earlier. For example, is Lava BLIP2 and another version of Lava. Cross-attention fusion. This approach connects the two parts, image encoder and large language model, more deeply, because we transfer visual information into the layers of the large language model. So it's already taken much more computing power, and its structure is more complex, but it allows us to get more fine-grained interplay between modalities. And the last one is end-to-end native modality. The hardest and the biggest approach out of these three is the most expensive. This training is the most long, but it gives us almost no limitation in what we can do whatsoever. It's very useful if you want to build something big, and it would be very adjustable to yourself. For example, it's OpenAI GPT and Google Gemini. There are no separate unimodal components. The model uses data, image data and text processing equally at the same time. So let's move to the BLIP2 architecture. BLIP2 main point is bootstrapping. Instead of training new model from scratch, we just take two frozen parts and fill the gap between them with the bridge called QFormer. This is a simple representation of its architecture. As you can see, the large language model and image encoder are frozen. To the QFormer, we pass queries, which are learnable, and some text, which stand for image caption, or example, image question about the image and answers to these questions. And in the end, we pass the output of the QFormer in a compatible form with large language model to receive an answer which we wanted to receive. There are different types of usage of BLIP2. I will cover them later. Also, as you can see, this image is split into two squares with dashed gray box, because it explains that training stage of the BLIP2 is split into two parts: vision language representation learning and vision language generative learning. Here is some information for the BLIP2 QFormer. As I said, it's split into two parts: the one that works with image and the one that works with the text. Image transformer part interacts with the frozen image encoder, and text transformer function as both text encoder and decoder, depending on the task. Here is more detailed representation of the QFormer. Here we can have the text input. It's being transformed into the tokens. On this side is text transformer. We have two self-attention layers, which actually are just one. We use masking technologies, different self-attention masks, to divide this self-attention layer to choose which tokens can see queries or other tokens, and then we can use masking for different training approaches. Here we have queries that are learnable and generated randomly at the start if you are not fine-tuning. They're also passed to self-attention first, then they are aligned in a specific way, and they're let's put it like they are given the task to extract features from the image which came from the image encoder as an output. They are mixed in the cross attention to align the features extracted from the image with the queries. Then they're moved through the feed-forward layer, and then we have the trained queries, which are queries that contain information about the image already. Then they're passed through the fully connected layer. This layer serves as a formatting layer because, as I said before, the output we get from the image encoder cannot be put into large language model, so we use this fully connected layer to format the queries to the large language model compatible format. And then we receive the text output. So this is more detailed description of these three layers. The first layer is applied to the queries. This allows the model to build relationships and dependencies among the queries. After the self-attention, we pass it to the cross-attention layer. The image embeddings act as the keys and values, and the queries act as queries in the attention mechanism. Cross-attention operation builds the attention weights to each image features and computes a weighted sum of the values. And then the forward layer. This is a layer that allows us to have more non-linearity in the process to get some more complex transformations of the query features. So a bit of description of the cross-attention block. In any standard transformer layer, an attention mechanism calculates an output vector of three inputs: queries, keys, and values. To put it simpler, queries are just trying to find the features, so they ask where are they, and the keys and values from the image encoder are exactly these features. They telling us what is in the image, and we trying to weight these two values, actually three values, to answer the question what is where. So the image encoder outputs thousands of features, and it's too many for the LLM to comprehend. So we simplify this raw image data and put it into 32 learned image queries. During the cross-attention step, each of the 32 queries are first to learn what combination of visual information is most important, and then they are passed to the fully connected layer. So the training of the BLIP2, as I said before, it's split into two stages. The first stage is representation learning. It has three goals, if we can call them like that. The main objective is to make the querying transformer learn which features are the most important and what is the most effective way to extract these features. So let's move through each part. So the first objective, we extract the features from the image. Let's call it a Z. Then the text transformers generates us a class token. Let's call it a T. Then we calculate the similarity between the Z and the T, and we have the similarity score of each pair of description of the image and the image features. And then we use a contrastive loss to pull positive pairs together. We use the unimodal mask in this stage so that the text tokens, these gray squares, can only see each other. And in order to create correct class token, and these colorful squares, they are the queries themselves. So, as you can see, the image and the text part is no longer connected because we masked the self-attention layer. And this way, we have a text transformer working with only the caption of the image, and the image transformer working with only the image encoder output. In this way, we have pairs of the generated class tokens and the generated or trained queries presented as a list of comparing of what is more relevant caption for the image. The second objective, image grounded text generation. The queries here must extract all necessary information to generate the text. So we no longer give the caption to the text transformer, and we apply multimodal causal mask. So here's how it looks. The caption of the image is not connected to the text transformer, so it doesn't know what is the right caption, and our goal is to generate it. So the text tokens can see the information in the query tokens, but they cannot see what will be generated in the future. So they can't see the future text tokens, and the queries can see all the text tokens. We connect the self-attention here in order to queries see the text tokens, and after that we pass an image. After this process, we get an image caption without needing to pass this caption we had already. And the last objective is image text matching. We feed the output query embeddings into a binary classifier and create the logits, pairs of yes or no questions. And the values is just a result of binary classification. What is the chance that image and the caption for the image is the right pair? So the image is captioned correctly. We use a bidirectional self-attention mask where text tokens can see both queries and other text tokens, and query 2 can see all the text tokens. We pass the image to the image transformer. The self-attention layer is now fully connected, not masked at all. We pass the caption to the image, and we add a binary classifier that will compare the text, the subjected text, and the image features, comparing if the features are the features shown on the image represent the caption we gave to the text transformer at first. So we have this image and this caption, and as you can see, this caption is not right. So we see the average scores, and the chance that this is a match is 0.25, and the chance that this is not match 0.55%. So the result of classification would be no, this is not the right caption. Generative learning. This is a step 2 of the training. We attach the large language model to the QFormer, and QFormer outputs vectors, produces output vectors to the LLM of the right format, and this is the main usage of the blip2. As you can see on this image, it's basically what I've shown on the very first slide. We just pass the image and trying to generate a caption for it. We have two usages here shown here. The one is when we have a prefix text. This is a text a user wrote and passed to the LLM encoder. So it also transforms into tokens and then being passed to the LLM decoder. If we have a prefix text, then the LLM decoder will try to finish the sentence we started. So it's full result will be enable overlord with a black cloak as a humanoid robot. But if we don't have a prefix text, then it will be set for the synthetic caption generation. It will just describe what does it see on the image overall. Because we don't give it any starting instruction. So you can see a few tests of what can Blip2 do. It can give you some facts, answer your questions about the image, but it can also generate some creative explains. For example, we need to generate a conversation between animals, and as you can see, it's capable of doing so. What's truly impressive that with only 2.7 billion, with only 100 million parameters, which is much less than the other models shown in this table, we achieve results that are better on zero-shot visual question answering benchmark, which proves the effectivity of this method and that building lightweight bridges is truly a useful practice in order to develop multimodal large language models. So here's some of my thoughts about what can I do in the future with multimodal large language models and Blip2 exactly. The first one is fine-tune it. I would like to take some special data and make it smarter in some specific region. For example, medical assistance or construction, so it could detect something on the X-rays or some defects on the manufacturing. The second is the real-time live communication. Imagine we have a camera. It can be put anywhere, in the robot, on the table, in your web camera, on the PC, or in your smart glasses. And we connect the Blip2 to the live feed of the camera, allowing you to anytime write a prompt question about anything that is going on the video. It will extract the current photo from the camera and try to answer your questions in the live format. And of course, the main one is to learn more about other similar models, Clip, Blip, Flamingo, etc. And that is all. Thank you for your attention. If you have any questions, please ask away. Or you can also contact me if you have any suggestions or any further discussions by this mail.
I think it was both presentations were very huge. So both of you presented very complicated systems, but very interesting and very impressive. Especially the last one. That means that if I have I have a camera, let's say a ball somewhere, and I can take a photo, and I can in fact ask what is on the picture.
Yes, that's right. That's the main concept. You just decide when you want to ask. It takes the screenshot of the live feed from the camera and answer the question.
For example, if I take, let's say, imagine that I have a camera about the port where the loading are going to be distributed. And if I take a shot and ask, give me the situation and then propose me how to distribute the loading to the other tracks. So you have an input from the camera,
Yes.
and then I can process with the other tools this current situation.
That's right. But I think you would need to fine-tune it for this specific task, so it would know better how to answer your question more structural and give you better answers overall.
I mean, generally, this is very important task because labeling is the most complicated and most expensive thing. So if you want to label, let's say 1 million images, then probably it's enough to label 100,000 images and then train them and then use it, and it's much better than data augmentation. Should be much better than data augmentation. So I think from this point of view, labeling is even they call it so-called pseudo labels, because on critical applications you cannot leave it to the machine. You need to confirm. First of all, you generate so-called label, and then you are waiting for the human to confirm this confirm. But then it's much easier if you have this kind of pre-processing and give you proposal. Is it this? Confirm this. Write 5 different lines about this.
Actually, the interesting part is that for the training of Blip2, there were used multiple web datasets, and the thing with web datasets is that they are very noisy, and their captions are not quite accurate. They can be completely wrong. So they already used this practice of generating synthetic captions for the datasets. They removed the noise using the previous model Blip, and extracted the features using Clip, and generated some of the synthetic captions to train the Blip2.
Okay, thank you again. So, any questions? I think I will leave it because we are rather long. It's more than an hour. So, thank you very much again, both students, and I wish them luck in their diploma and bachelor thesis. I think you made a good start, and I feel that you are interested in this, and that's the main issue. That not to do a diploma thesis or a bachelor thesis just because somebody wants to do it, but because you should be interested in this domain. And I'm very sure that if you will be interested and you will be good in this, you will not be hungry, because AI is here and will be for a while. So thank you again for coming, and I want to just remind you that next week we have a very interesting visitor from real world application. It's our former student, and our former student next week will be talking about vibe coding. So vibe coding is a very big issue. So if you are interested in this, then you are very welcome to come next week, Friday, again here. And he will be talking and he will be presenting one of the platform for vibe coding. But secondly, he will also show you some big problems with the vibe coding, which is a cybersecurity issue. So if you are interested, you are very welcome. Thank you again, and if you are thinking to join, then the association, you are very welcome. Thank you. Thank you. Have a nice weekend. Thank you.